Okay, it looks like your title changed. I'll read the one here.
Yes.
Oh, I have to go full screen. Okay, our next speaker is Philippe Priolet from ESO and other places. He's going to tell us about exozodis, interferometry, and radiative transfer.
Yes, can you hear me? So yeah, my name is Philippe. I work in Grenoble at IPAG, and I'm a last year PhD student. And today I wanted to talk about exozodis, exozodiacal dust. Oh, sorry, I need the system. Perfect, sorry. So exozodiacal dust, but also about interferometry and radiative transfer, which are all very important things to understand exozodiacal dust. So first of all, what is exozodiacal dust? We've heard it being mentioned during some of the talks, but what is it actually? So we've seen a lot of the images of debris disks. Typically, what people call debris disks are the coal dust in the outer regions, so what in this diagram is called the outer belt. But there's also dust in the inner regions of planetary systems. So they're typically distinguished in two components, what is called warm dust and hot dust. So warm dust is more or less in the habitable zone of the system at around 300 Kelvin, and hot dust is much closer to the star at a few stellar radii, and it's much hotter, close to the sublimation temperature of the dust grains. So what do we know about this inner dust, this exozodiacal dust? So there's very little that is known. It is typically detected with interferometry, but we have very little spectral information on this dust, and so we have very little information on the dust properties. We also don't really know the spatial distribution of grains in this region, because what is done typically is that we measure the integrated flux that's coming from this region. So we don't know a lot about it. Why is it interesting? So we've heard a lot about it during this conference as being a potential threat to HWO and to direct imaging missions. But I want to make a point that it's also an interesting object to study in itself. It's not just a hindrance, but it's actually quite interesting, and it can tell us a lot of things about the system. So here I show some detection statistics of hot dust detected in the H-band. And what we have is the H-band excess frequency in function of stellar age. So you can see that a lot of the hot dust is detected around very young stars. But then, as we increase in stellar age, we have more or less a constant rate of detections. So there is a presence of this dust regardless of stellar age. And why is this puzzling? It's because dust in these regions, especially hot dust, should have very short lifespans. So the dynamical timescales in this region are very short, and so the dust should collisionally erode very quickly. But also, studies have shown, have hinted that this dust may be composed of submicron sized grains, and so they should be blown out by radiation pressure in this region. So this poses the question, how do we explain this dust? And so it poses questions on the replenishment mechanisms, what is producing the dust, and also if there is a trapping mechanism that allows the dust to stay in this inner region. Furthermore, this dust can tell us a lot about the architecture of planetary systems. If we can constrain the replenishment mechanism, we can understand things about the architecture of the system, the presence of planets. Also, clumps in the dust could hint at the presence of planets. So it's an interesting object in itself. So here I wanted to talk about my first work during my PhD, which is around beta peak, and also to sort of show you how we detect this dust in practice with interferometry. So for this, I am using the VLTI, which is the interferometer at the VLT. And in particular, I'm using the Matisse instrument, which observes in the L band, L, M, and N bands, but here I only show the L band data. So what I'm showing here is the squared visibility in function of spatial frequency. That's the plot on the right, on the top right. And what is the visibility? It is linked to the Fourier transform of the intensity distribution of the object. It is the modulus of the Fourier transform. So here I show the squared visibility. So you can see if we only had a star, we would have the blue curve at the top, that would be just the star, but we have actually visibilities that are lower than just the star. And this means that we're resolving something within the field of view of the instrument. Just to give you an idea of the size of that field of view, for this data set, it's about 1 AU. So we're resolving something within 1 AU of the star. And something I wanted to point out is if we look at the structure of the data, so the 6 packets that we see in that plot represent the 6 baselines, the 6 possible combinations of the 4 telescopes. And inside those packets, we have the spectral channels for Matisse, so in the L band around 3.4 microns. And as you can see, the points inside a packet are very sort of compact. They follow a certain tendency, and this indicates that the noise in the data is very correlated for spectral channels. And so we developed a method to estimate what these correlations were in Matisse data, because here we are really at the limit of sensitivity of Matisse. So we really got to understand the errors properly. So we developed this method, and what we found was that Matisse is very, very strongly spectrally correlated. So these are the squares along the diagonal. That's the correlation in the spectral channels, and it is very close to 1. So very, very strongly correlated. And I also show this to show the impact that this had in the model fitting. So we included in the model fitting these covariance matrices. And so if we don't take into account correlations, typically the best model that is often used for these types of observations is something that's overextended and homogeneous, and the only free parameter is the flux ratio, the ratio of the dust over the total flux. But when we take into account correlations in the model fitting, we can actually complexify the model even further. And so here I show one of these models that we fitted into beta peak data. So it's just a Gaussian on the sky. It's still a very simple model. It's a Gaussian with a certain full width half maximum, a certain inclination, and it's oriented in the sky in some type of way. And it also has a flux ratio. And so what we find is that when we take into account correlations, we get a fit that's very different from something that's overextended. So we get something that's very compact. You can see here the full width half maximum. It is a fraction of an AU. So we're really, really at a few stellar radii from the star. It is very inclined. And something that was quite surprising for us is that it is misaligned with respect to the outer disk. So here you have an image of the outer disk. This is the cold debris disk. And we find a misalignment of about 60 degrees with this outer debris disk. So this is quite interesting, as it poses questions on the replenishment mechanisms. It can give hints, because if you believe that the dust is produced in the outer disk and then it follows some transport mechanism inwards, then you would expect the dust to be on the same plane as the outer disk. But that's not what we see for beta peak. So these are hints this can give hints on the replenishment mechanisms. So this is my work on beta peak and on Matisse. So what we found with Matisse is that correlations have a very strong impact on model fitting, and that especially for exozodiacal dust, we really need to take them into account. That Matisse data and interferometric data in general is highly correlated, and especially between spectral channels. This is also something that was found for another instrument at the VLTI, which is called gravity. So this is something very common to long baseline interferometry. And finally, I didn't mention this point too much, but calibration induces very strong correlations on the data. So when you use a calibrator star for your measurements, you induce these very strong correlations. You can ask me about it afterwards. And what did we learn about the exozodi? So first is that the dust is very close to the sublimation region of both silicates and carbonaceous grains. So this is the plot that I show here on the bottom left. So we have the temperature of carbonaceous grains in function of grain size and distance to the star. In white, I show the sublimation region, and the shaded area represents more or less where we would find this dust. So really, really close to the sublimation region. Also, we find that the dust must be composed of very small grains, because we also fitted models with a spectral dependency. And if we make an assumption on the temperature of these grains, we can use models based on me theory to sort of estimate what the size of these grains would be. And as you can see here, for our measurements, which are the colored areas, bars, for 3 different temperatures, we need very small grains to be compatible with the model. So we have very small grains, very close to the sublimation region, which are misaligned with respect to the outer debris disk by about 60 degrees. So a very big misalignment. And now for the last part, I wanted to talk about these 3 stars that I'm working on, HD113766, HD112555, and Eta Corvi. So we obtained multi-wavelength interferometric observations of these 3 stars with Matisse in the L, M, and N bands, Gravity in the K band, and Pioneer in the H band. And what I show here are the first preliminary results. So we have a detection for HD113. We have a detection in all 3 at all 3 wavelengths. HD172, we also have a detection at all 3 wavelengths. And for Eta Corvi, we detected in the L band, where we expect the dust to be brightest if it's a thermal emission. So now we have multi-wavelength observations, and the question is, how do we model them? In the previous section for beta peak, I only tested geometrical models. There's no radiative transfer. There's no physics behind them. And so for this, we developed a code, which is called PI Grader, based on the code Grader, which my PhD supervisor developed. And the idea is to make an open source radiative transfer code that supports both thermal emission and scattered light observations. So as I mentioned, we model the thermal flux and the scattered flux for certain grains, certain composition of grains, based on the me theory. And so here I show some of these properties, so the absorption efficiency, the scattering efficiency. So we model these properties. Then we can calculate the temperature of the grains based on grain size and distance to the star. And we can calculate then the thermal flux and the scattered flux. So we can produce SEDs. You can see here an example of an SED with the scattered flux and the thermal emission for a certain spatial distribution and grain size distribution. But we can also calculate images. So here you have scattered light images, the thermal emission, and the total flux at 2 wavelengths, at 1 micron where the scattering dominates, and at 3 micron where the thermal emission dominates for this example. So what's cool about this code is that you can create your own models. So you can input your own dust density distributions, your own size distributions, your own phase functions, and the code will work just as well with that. And you can even input empirical models. So if you, for example, have lab measurements of phase functions, you can input them into the code. The code will interpolate these measurements, and it will do the radiative transfer with them. And just the final mention, there's this code for long baseline interferometry called OA Modeler. It is used to fit interferometric data. So it takes some observations, and it fits geometrical models to those observations using some sort of fitter, like an MCMC. And so we're integrating PI Grader into this fitting code. So you should be able to very easily fit interferometric data with actual physical properties with radiative transfer. And finally, I just wanted to say that I'm a last year PhD student, and I'm going to finish in the fall, and I'm looking for a postdoc. So if you're interested in any of this, let me know. Thank you.
So we have time for a couple questions.
Hello.
It's not on, I don't think. Oh,
I'm Yu Zhaling from University of Arizona. So you mentioned a beta peak exolody have a 60-degree misalignment, right? How do you have a error bar estimation?
Yeah, it's very small. So it is, you can see it here. It is about 1 degree in error.
So it's 60 plus and minus 1?
Yes. Yes, correct.
Yeah, Philippe, I wanted to ask about that a little more. I mean, the star is fast rotating, so it should be rotationally flattened.
Yep.
And so would this inclined inner disk be stable, orbiting so close to a very oblate star?
Oh, that's a great question. I do not, my expertise is not in dynamics. I wouldn't be able to answer that. I know that we flattened that, we modeled the star as a fast rotator with a certain obliquity. I don't know about the stability of that. I know that there's a study by Hervé Bust that tried to explain the reservoir of exocomets, and they found that exocomets could be stable to about a fraction of an AU. I don't have the exact number. Not stable, but they could enter this region. So, yeah. That's also a question on the trapping mechanisms, what allows the dust to stay there.
All right, let's thank Philippe again.
Thank you.